Hello, I'm going to go through the answers to the energy levels in spectra questions, okay? The mark scheme is attached, but if you struggle with it, you can follow my instructions. So, number 1 says, the transitions shown in the diagram represent photons being emitted in the ultraviolet, visible and infrared radiations sections. Which region does each one represent? So the smallest jump will be the longest wavelength, which is A. So that's infrared. This is visible light, and then this is ultraviolet. Biggest jump, most energy, shortest wavelength. So that's your answer there. Next. 2 ways to excite hydrogen atom are by collision of free electron or by absorption of a photon. Explain why for a particular transition the photon must have the exact amount of energy, whereas a free electron only needs a minimum amount of energy. Okay, so what you need to say is an exact amount of energy is needed to move to a higher energy level. 1 mark. Okay, then you need to say all of the photon energy. Oh, I spelled that wrong, sorry. Photon energy, okay, is absorbed. So that's why you have 1 photon. Okay, but the electron can transfer part of its energy. Okay, 3 marks. Says the sample of the cesium is exposed to photons emitting, and they've got this threshold frequency. Determine when any of these transitions will produce photons that will cause electrons to be emitted. So basically I want to find out how many electron volts is that frequency and then calculate the differences in these. So the first one, phi equals HF. Okay, so I'm going to work out what my phi is in joules. So it's 6.63 times 10 to the minus 34 for H times that frequency. That gives me 3.38 times 10 to the minus 19 joules. If I divide that by E, it will give me the value in electron volts, which is 2.1. Now I need to see if any of these jumps are 2.1 electron volts. So if I do A, that's 1.5 take away 0.85, which is 0.65, so no. Okay? If I do B, that's 3.4 take away 1.5, which is 1.9 electron volts. So no, that's not big enough either. So if I do this one, 13.6 take away 3.4 gives me 10.2 electron volts. And that one is big enough to meet this. Okay, so you can do all your working out here for that. That's what your 3 marks are for. Okay, and then D, photons with each of energy 12.1 electron volts are incident on the surface of the cesium sample. Calculate the maximum speed of the electrons emitted. So I need to calculate their kinetic energy. So my photon energy is equal to phi plus Ek. I want Ek. So Ek is equal to HF minus phi. My HF is for the photon energy, which is 12.1 electron volts. So I need to convert that into joules by times and by E. And I need to take away my phi, which I calculated here. That gives me a kinetic energy of 1.598 times 10 to the minus 18 joules. Can then rearrange the kinetic energy equation, which is Ek equals half mv squared, for V. So V equals the square root of 2E over m. So 2 times this value and then divide by the mass of an electron, which is 9.11 times 10 to the minus 31. And the value you should get is 1.9 times 10 to the 6. So they move really, really fast. Okay? Next, question 2. The diagram shows some of the energy levels for a hydrogen atom. Free electron of kinetic energy 20, 0.0 times 10 to the minus 19 collides with the hydrogen atom state. Kinetic energy of the free electron after the collision is, well, it collides with it, is excited from the ground state to the first. So we're going from here to here. So what we need to do is from this energy, we need to take away how much that energy that is. So you're going to do 21.8 times 10 to the minus 19, take away 5.4 times 10 to the minus 19. So this is the energy in, and this is how much energy this electron gets. The difference is 3.6 times 10 to the minus 19 joules, which is B. Describe how the concept of energy levels is useful in the explanation of line spectra. So we're talking about here that only certain energy changes are allowed because of the different gaps. So these ones, yeah? So a line is produced when the transition between energy levels leads to a photon of specific wavelength being emitted. Okay? Right, the diagram represents some energy levels of mercury. So we've got our energy levels there and we've got some information here. So you can keep an eye on what these are whilst I do the answers. What is the ionisation energy of joules of the mercury atom? So the ionisation energy is 10.4 electron volts. So I need to just convert that into joules. So I just do 10.4 times 1.6 times 10 to the minus 19, which gives me a value of 1.66 times 10 to the minus 18 joules. Determines which transition corresponds to an emission of radiation of wavelength 141 nanometers. So I need to work out how much energy that is with the wavelength equation. So it's 6.63 times 10 to the minus 34 times 3 times 10 to the 8 over this wavelength, 141 times 10 to the minus 9 meters. This gives me an energy in joules of 1.4 times 10 to the minus 18 joules. I need that in electron volts, so I divide by E, which gives me 8.8 electron volts. And I then go back to this diagram and figure out which one is 8.8 electron volts. And it's this one. Okay? So 1.6 to 10.4. Okay? State the region of the spectrum where would you expect to find radiation of this wavelength. You probably don't know this because we haven't really done waves yet, but it's ultraviolet. Okay, you can just look that up. Question 4. Here's some more energy levels. The diagram represents some of the energy levels of an isolated atom. An electron with a kinetic energy makes an inelastic collision with an atom in the ground state. Calculate the speed of the electron just before the collision. So we're going to use that kinetic energy equation again. Rearrange for V, 2ek over m. Put your values in. So you've got 2 times 10 to the minus 18 over the mass of an electron, 1.99 times 10 to the minus 31. And you should get a value of 2.1 times 10 to the 6 meters per second. Next, show that this electron can excite to an atom to level 2. Okay, so if we look at our levels, we've got 2 times 10 to the minus 18, and our level 2, so what are we doing? We're going from ground state to here. Okay, so if we work out what the difference between these two energy levels are, we've got 2.18 times 10 to the minus 18 minus 2.42 times 10 to the minus 19. Okay, that equals 1.93 times 10 to the minus 18 joules. Okay, which is less than 2, so it can make the jump. Calculate the wavelength of the radiation emitted when an atom falls from 2 to 1. 2 to 1. So first thing you need to do is calculate the change in energy. So you've got 5.48 times 10 to the minus 19, take away 2.42 times 10 to the minus 19, which equals 3.06 times 10 to the minus 19. Okay? What you're then going to do is put that into E equals hc over lambda. We want lambda, so that's hc over E. H is 6.63 times 10 to the minus 34, C is 3 times 10 to the 8, and you can sub in this value here for joules. And you should get 6.5 times 10 to the minus 7 metres, which is in the red region, visible light. Calculate the minimum potential difference needed for this to be ionised. So E equals QV. We want V, which is E over Q. To ionise, you need 2.18 times 10 to the minus 18 joules, and you're going to divide that by the charge of an electron, 1.6 times 10 to the minus 19. And you get 13.6 electron volts. Sorry, ignore the electron bit. Sorry, 13.6 volts. Next, the diagram shows some energy levels of a hydrogen atom. Explain how changes of electron energies can produce line emission. So first of all, the electron is excited. Okay. Then it is excited into a discrete energy level. Okay. Then the electron de-excites. Okay. A photon is emitted, which has a definite wavelength, which is the line. Okay? Next. What is meant by ionisation? It is when an electron is removed from an atom. State the energy in joules required to ionise a hydrogen atom. So it's this, 22 times 10 to the minus 19. Minus 19's there. Calculate the minimum frequency of radiation that can ionise that. So E equals HF. We want F equals E over H. So we sub in this value for E and divide by H. And you should get a value of 3.3 times 10 to the minus 15 hertz. Explain what happens to an electron in the ground state of hydrogen atom when it receives a radiation of frequency greater than the minimum frequency. The ionised electron will have kinetic energy. Okay? Calculate the wavelength of the radiation emitted when an electron falls from N3 to N2. N3 is here and N2 is here, so you just need to calculate the difference in energy. So that is going to be, change in energy is 5.4 minus 2.4 in joules. So that is 3 times 10 to the minus 19 joules. Then you use E equals hc over lambda. You want lambda, which is hc over E, which gives you, so here's your energy, so that gives you 6.6 times 10 to the minus 7 metres. State what happens in an atom when line spectra are produced. I mean, it's the same answer as we've used before, so you can just copy those over. Okay. Then in B, you've got some energy levels, and it says calculate the ionisation energy of a lithium. So this is 5.4 electron volts. So you need to do 5.4 times 1.6 times 10 to the minus 19, which gives you 8.64 times 10 to the minus 19 joules, because that's how much energy you need to get from here out. An excited lithium atom may emit radiation of 6.1 times 10 to the minus 7 meters. Show the frequency of this is that value. So you're going to use E equals HF. Sorry, I lie. You're going to use F equals C over lambda. Okay, so 3 times 10 to the 8 over 6.1 times 10 to the minus 7 gives you that value. Calculate the joules, energy in joules of each photon of this radiation. So now you use E equals HF. So you just do H times that energy, that frequency, and you get 3.2 times 10 to the minus 19 joules. Draw on the diagram the arrow between two energy levels which show the transition for 1.8 electron volts. So 1.8 electron volts is the difference from here to here. So that's that one, so that's IV. For V, it says two transitions emit similar radiation. One of them is B to D, which is the other one. The one that's similar to this is D to E. Same value, really, if you calculate the difference between the two. And a transition between two energy levels gives the longest wavelength. That's the smallest amount of energy. So that's B to C. So that's the last one, BI. Okay. So these are D to E and was it B to C? Yeah. Okay. Hope they found that useful. Thank you.